Hi everyone, I'm Gon from KAIST. I'm presenting our work titled HashNWalk, Hash and Random Walk based on anomaly detection in Hyperedge streams. The outline of this presentation is as follows. Hypergraphs are everywhere. Hypergraphs consist of nodes and hyperedges, where each hyperedge is a subset of any number of nodes. Group interactions, which are naturally represented by hypergraphs, arise in various areas in our life. Collaborations of researchers, co-purchases of items, and joint interactions of proteins, to name a few. In many cases, hypergraphs evolve over time, and in such scenario, we model the hypergraph as a temporal hypergraph, which is a sequence of temporal hyperedges. Each temporal hyperedge is a pair of a set of nodes and the timestamp it appeared. Note that temporal hyperedges consisting of the same set of nodes can appear at different timestamps. In this work, we focus on the problem of detecting anomalous temporal hyperedges in the given temporal hypergraph. Specifically, we focus on two intuitive aspects of anomalousness. First, unexpected hyperedges consist of unnatural combinations of nodes, and bursty hyperedges repeat in a short period of time. Formally, the problem of hyperedge anomaly detection is to detect anomalous temporal hyperedges whose structural temporal properties deviate from general patterns in near real time using constant space. To this end, we utilize the random walks on the hypergraph. Typically, a random walk on a hypergraph is formulated as a three-step process. Given the current node U, it first selects a hyperedge E that contains the node U. Then it selects a node V from the hyperedge E uniformly at random. Finally, it walks from node U to node V. However, this random walk is proven to be equivalent to the random walks on a click expansion of a hypergraph. Since the higher order information of the hypergraph is damaged during the transformation into the click expansion, such random walk hardly captures the higher order structural relationships between the nodes. To this end, the edge-dependent vertex weight-based random walk has been proposed recently. Instead of selecting a node from the hyperedge uniformly at random, it samples a node with probability proportional to the edge-dependent node weight, which is a weight of a node specific to the hyperedge. Previous studies have theoretically and empirically proven that considering the edge-dependent vertex weight to the random walk on a hypergraph effectively captures higher order information of the hypergraph. We propose HashNWalk, a fast and space-efficient algorithm for detecting anomalies in a hyperedge stream. First, HashNWalk uses a random hash function to merge nodes into M supernodes. Then, the proximity between the supernodes are summarized as a concise summary matrix P', which is a matrix of a transition probability of the edge-dependent vertex weight-based random walks between the supernodes. This summary is updated in near real time for every new temporal hyperedge. Once the hypergraph summary is updated, it is compared with the previous summary metrics. We define anomaly scoring functions, score U and score B, to detect unexpected and bursty temporal hyperedges respectively, to numerically measure the anomalousness of the new temporal hyperedges in two aspects. To evaluate HashNWalk, we use various hypergraphs including email inloan, DBRP, and site patent datasets. We evaluate HashNWalk in 3 real-world and semi-real-world datasets with 4 state-of-the-art baselines. We can see that the proposed method is accurate and fast. We also conduct a case study using a DBRP hypergraph, where each node is an author and each hyperedge is a publication. Using the defined anomaly score functions, we can detect some authors whose co-working styles deviate from the general pattern. For example, Dr. Fu and Dr. Sakamoto differ in their co-working patterns, which can be verified by their number of co-authors and the number of co-worked papers. In the site patent hypergraph, each node is a patent and each hyperedge is the set of patents that are cited by a patent. We can visually verify that unexpected and bursty hyperedges have different structural patterns, and qualitatively, we can find some patents whose citation patterns are very different. In conclusion, we propose HashNWalk, an online anomaly detector for hyperedge streams. HashNWalk is fast, space efficient, and accurate, and these properties are theoretically and empirically verified in the paper. Codes and datasets are available in our GitHub page. Thank you for listening to our presentation.